This is the lecture for the 5th module of Unit 5. In Module 5, we look at aspects of and do calculations concerning acid-base titrations. It's well to review briefly the anatomy of a titration before we carry on. In general, you have an analyte, which for this discussion will be a base or an acid, generally of unknown concentration, and you are attempting to determine its calculation by the addition of titrant, which is also a base or acid and which is of known calculation. What we will do here is look at calculations involving analytes for which we know the calculation. And review the applications that result from what we learned. Strong acid, strong base calculations and titrations, if you know the concentrations of the species involved, are very straightforward. For example, consider titrating 1 molar hydrochloric acid into an analyte of 35 milliliters of 0.3 molar sodium hydroxide. Right. Before the titration, we can say, it's a hydroxide solution of strong base, so the pOH is the negative log of 0.3, which is 0.523, and pH is 14 minus 0.523, call it 13.4H. You can also do a calculation to determine moles of hydroxide present, 0.3 moles times 0.035 liters is 0.0105 moles. Alright, assume 50 milliliters of the hydrochloric acid is added. In this case we have a volume of 85 milliliters. Simply sum 35 milliliters and 50 milliliters. 50 milliliters has been added to the analyte. 0.05 liters times 0.1 mole. Convert to moles of sodium hydroxide formally shows that 0.005 moles of sodium hydroxide are neutralized by addition of the HCl. HCl and an AOH react in a 1-to-1 ratio. And there must be 0.0055 moles of hydroxide remaining. We can convert that into a concentration, 0.0647 molars, find a pOH, and then a pH. pH is 12.81 at this point, which you might not call a lot of change. pH is changed by 1. Now, contrast to the equivalence point, where you know all the sodium hydroxide has been neutralized. You expect a pH of 7, and you can start with the moles of sodium hydroxide, which is to say the molarity times the volume again, convert to moles of HCl, divide by HCl volume, and readily calculate liters and milliliters of HCl that have to be added to reach the equivalence point. Remember, the equivalence point is when all the moles of sodium hydroxide you've started with have become neutralized. Beyond this point, after addition of 105 milliliters, you are essentially, adding strong acid to the mix and just diluting a strong acid solution at that point. Now, if you consider a titration curve for this situation, which is a graph of pH versus volume of titrant added, as our calculations have shown that the curve should be flat initially, not a lot of change in pH, but it becomes very steep as we near the equivalence point. There's a steep decrease to 7, and then the curve flattens out again. as excess solution is added. Excess acid solution is added, I beg your pardon. Alright, so flat curve for quite a range of the titration, in which case but then the pH starts to drop very steeply. Oh, and notice the equivalence point, beg your pardon. Notice the equivalence point into the titration is pH is 7. You notice the particular behavior of the curve around the equivalence point, at the equivalence point. Alright. Let's consider titrating a strong acid into a weak base by comparison. Here we will titrate 25 milliliters of 0.1 molar ammonia with 0.1 molar hydrobromic. Now remember, ammonia is a weak base, but hydrobromic acid is a strong acid. We'll dissociate into H plus and bromide. Bromide is a spectator ion I'm going to ignore in much the same way we ignore the sodium in the last example. As the titration goes on, the reaction is ammonia plus hydronium goes to ammonium plus water, or you could write it NH3 plus H plus goes to NH4 plus. Alright, now let's do an equivalence point calculation. We can find the original moles of NH3, molarity times volume. Since this is a reaction with 1-to-1 stoichiometry, that requires 0.0025 moles H plus, and note that we'll produce 0.0025 moles of NH4 plus. Volume added, 0.02, is moles divided by molarity of the hydrobromic acid solution. 0.0025 divided by 0.1 is 0.025 liters, or 25 milliliters. Which means at the equivalence point, the volume of the solution will be 0.050 liters or 50 milliliters. Right. It is important to note at this point that ammonium is a weak acid, and the solution will hence be acidic at the equivalence point. Ammonium is the conjugate acid of a weak base, and itself, as we have seen, has weak acid properties. Alright, at this point, the concentration of ammonium in the solution is 0.0025 moles over 0.050 liters, or 0.050 molar. And the problem of finding the pH reduces to, what is the pH of a 0.050 molar ammonium solution? Alright, you have seen calculations of this type. We can find a Ka by taking Kw and dividing it by Kb for ammonia. 1 times 10 to the negative 14 gets divided by 1.8 times 10 to the negative 5 to produce 5.6 times 10 to the negative 10. Remembering this is our reaction, ammonium plus water makes H plus, or hydronium plus NH3. Removing water, writing the equilibrium expression in terms of the solutes gives H plus times NH3 over NH4 plus for the equilibrium expression. We can build an ice table in which there are no H plus and no ammonia. Initially, remember, we are at the equivalence point where all NH3 has been neutralized, at least to a first approximation. And if we make the approximation that the change in the ammonium concentration is small, we'll just call that 0.050. And solve for x, it's 5.3 times 10 to the negative 6, which produces a pH, negative log of H plus, negative log of 5.3 times negative 6, of 5.28. In other words, the equivalence point of this titration, unlike the preceding one, is not at 7. Now let's go back and consider things before the equivalence point. Alright, now that we know where the equivalence point is, we just pick some point before it when only 12 milliliters of hydrobromic acid have been added, for example. We can take molarity times volume of the hydrobromic acid, convert to moles of ammonia formally, 1:1 mole ratio, find that 0.0012 moles of ammonia have reacted at this point. Alright, this leaves 0.0025. We've already calculated moles of ammonia starting. Minus how many are left? 0.0012. Gives 0.0013 mole of ammonia remaining. 0.0012 moles of NH4 plus and produced. Alright, so we don't have a pure ammonia solution, quote unquote. We don't have a pure ammonium solution, quote unquote. We now have a solution partway through the titration where some ammonia and some ammonium exists. Oh, the overall volume, and we'll call that 37 milliliters, 0.037 milliliters. It's straightforward to calculate concentrations of ammonia and ammonium at that point. And you can identify this as an acid and its conjugate base, the two components of a buffer. Calculating the pH any time, well, after the titration has started and before the equivalence point, produces a buffer type situation. Concentration of ammonia then is 0.0351, ammonium is 0.0324. We can take the Ka of ammonium, which we've already determined, and solve for H+. This gives X is 5.2 times 10 to the negative 10, which is the H plus concentration and a pH of 9.28. Or we can take Kb for the conjugate base and solve for a hydroxide ion concentration. That would be X in this case. Notice that in this case ammonium is in the numerator and ammonia is in the denominator. That gives X as 2.0 times 10 to the negative 5. That's a hydroxide ion concentration. So that leads to a pOH of 4.7, but a pH of 9.3. Within round off, the two pHs that result from this are the same. Alright, now let's look at our titration curve. We start at a high pH, the pH of an ammonia solution. However, we see a more gradual downward slope as opposed to the flat curve, which becomes steep, that we saw when titrating a strong acid with a strong base. This region is the quote-unquote buffer zone. We reach an equivalence point, and notice that the equivalence point is below 7. After the equivalence point, we're adding excess strong acid, and once again we see a steep curve that flattens out. Or we would see, and we would see that, but we would see calculations to support that if we made the appropriate dilution strong acid calculations. Okay, consider the titration of formic acid, which is a weak acid, with sodium hydroxide. 50 milliliters of 0.10 molar formic acid is titrated with 0.10 molar sodium hydroxide. What is the pH at the equivalence point? Alright, you'll need a Ka for formic acid to do this problem. And you should consider, before starting, the reaction that will take place. Sodium hydroxide will react with formic acid. If you neutralize it all, what you will have left is sodium and formate ion. We predict a basic endpoint when we titrate this weak acid with a strong base. Alright, your calculation, molarity times volume, convert that to moles of formic acid to moles of hydroxide. Shows that 50 milliliters of hydroxide solution, or 0.050 liters, will have to be added. Therefore, the final solution has a total volume of 0.05, the volume of the acid, plus 0.05, the volume of the hydroxide, or 0.1 liters, 100 milliliters. All formic acid is used up in this titration. The first is approximation. We have no excess hydroxide. We have formate. Moles of formate are equal to moles of formic acid that reacted. There are 0.0050 moles of formic acid originally. That goes to 0.0050 moles of formate produced. Alright. Divide volume to obtain the molarity. 0.05 moles divided by 0.1 liter is 0.50 molar. 0.05 molars, beg your pardon, let me correct that. Problem reduces to, what is the pH of a 0.050 molar formate solution? Alright, now consider the formate reacting with water. As a weak base, it will produce hydroxide and neutral formic acid molecules. Our ice table will look like this. Initially, no concentrations of the formic acid and hydroxide. 0.050 concentration of the formic acid. Concentration of hydroxide is X once we write down all the equilibrium concentrations. And we will naturally roughly assume that 0.050 minus X, the equilibrium formate concentration, is around 0.050. We'll see that that's justified when we find Kb for the formate by dividing Kw by Ka for formic acid. That's 1 times 10 to the negative 14 over 1.8 times 10 to the negative 4 is Kb. Kb is 5.6 times 10 to the negative 11, very small. Alright. 5.6 times 10 to the negative 11 then is x squared over 0.05 gives x is 1.7 times 10 to the negative 6. That is a hydroxide ion concentration. Gives a pOH of 5.77, and again the pH will be more than 7 after we find the pH by taking 14 minus 5.77. pH is 8.23, indicating, well, as we know, a basic solution. Alright, so if you titrate a weak acid, your endpoint will be basic, greater than 7. You have a buffer zone before the endpoint. We have not done any calculations, but the buffer zone is will be a combination of formate and formic acid. So again, we have a gently sloping curve here, and then after we are adding strong base after the endpoint, once again we see a steep curve that flattens out. Alright, let's end this section with some thought about indicators. Indicators, as you know, are substances that change color, indicating when, well, hopefully indicating the equivalence point. Indicators change color at a particular pH. They are themselves weak acids. In general, if you're titrating a strong acid with a strong base, because of the steep change in pH around the equivalence point, any indicator with a pK between 4 and 10 will do. If we titrate a weak acid, however, the pH at the equivalence point is greater than 7. So an indicator that changes colors at pH greater than 7, such as phenolphthalein or thymol blue, must be used. If you titrate a weak base, the pH at the equivalence point will be less than 7. You'll have an acidic solution, and you'll want an indicator such as methyl red or bromo cresol with a pK less than 7 that changes color for acidic solutions. All right, this concludes the lecture on acid-base titrations.